Hello, students. Welcome back. I'm glad to have you here. We are moving on to Chapter 16. So before we start talking about Chapter 16, let's talk about a few things that are due. So this week, everything is due on Sunday night. So please take a look at the calendar I sent out. So please listen to all of these notes, review them, look at them. We're completing Chapter 16 this week. You do need to make 2 posts on the discussion board on Wolf Den. So if you go to the discussion forum on Wolf Den, you can either work out one of the 4 practice examples. So in here, there are examples. I ask you to stop the video, do the example. Please solve one of them for your friends. Hopefully your friends have already done this, that they can check your answers. So if you want to work out one of those examples, great, that can count as one of your posts. Maybe you can ask a question about content you don't understand, and then maybe a student can answer that question. So you need to make at least 2 good discussion posts. And if you want bonus points, you can make more than 2. I'm not necessarily putting a limit on how many you can post, but obviously a reasonable number, so that other students have an ability to respond to each other. And then there is also an experiment that goes along with Chapter 16. So please look at Wolf Den for that assignment. So let's start by talking about thermodynamics. So we talked about thermodynamics a little bit last semester. We talked about the enthalpy of the system. In all of our work that we've been doing, we've been looking at different chemical and physical changes. We've been looking at the kinetics, the equilibrium, how fast or how far things will go. Now we really need to look at the big picture. So the big picture, the only way that things will actually happen is if we take a look at the entropy, the driving force behind this chemical and physical change. So we talked about kinetics. Kinetics is in the middle of what we're talking about. So kinetics, we talked about how fast are things going? What are the intermediate steps? What does it take to get there? Thermodynamics, though, only talks about the initial and final steps. It only talks about, is this spontaneous or not? Okay, spontaneity does not mean speed. Do not relate those to each other. Is it spontaneous? Will it go forward without adding any extra heat or not? Okay, that's the only thing we talk about when we talk about spontaneity. So thermodynamics talks about the difference between the reactants and the products. So that always means you're going to see some change, right? Some delta. It'll always be our products minus our reactants, okay? We don't care about those intermediate steps that we have going on. So thermodynamics predicts whether a process will occur under a given conditions. Is this spontaneous? So spontaneous means it's going to go. We don't need to add any extra energy. Non-spontaneous, you would obviously need to add energy to get it started. So spontaneity, you would need to compare the chemical potential energy of the system before the reaction with the free energy of the system after the reaction. So you're comparing how much energy was there to begin with and how much energy is there now. You can compare those. What has to happen is the energy has to be greater. It needs to give off more energy. It needs to be more energetically favorable to be a product for this reaction to occur. Okay? It doesn't have anything to do with how fast it's going to happen. It just has to, is this going to happen? Is it more energetically favorable for this reaction to occur? So some of us have diamonds on our fingers. Our diamond will actually convert into graphite because graphite, as you can see, diamond is highly ordered. There are all these bonds that are there, whereas graphite is less ordered. We always want to get to a less ordered system. So it is spontaneous. Your diamond will spontaneously change into graphite. This process occurs so extremely slowly that we don't even have a time frame for it. So you don't need to worry about the diamond on your finger turning into graphite, but it does end up happening. This is a spontaneous process. This is what we're talking about in this chapter. We're talking about the entropy. So how we are going from an ordered process to a non-ordered process. Think about your bedroom. It most likely very easily goes to an increase in disorder. You clean it up, the next time you look, it's a mess again, right? Our universe is always going to a state of disorder. So when we talk about spontaneity, um, any spontaneous process is irreversible because it releases energy. So it is not going to go backwards in the opposite way. If you take a look at this car, this nice, shiny, brand new car, right? It's spontaneously rusted over time. It is impossible for us to go back to this nice, shiny car. It is non spontaneous. Doesn't mean it won't happen. You obviously could make it go back, but obviously you would need a large input of energy in order to make it a non spontaneous process. So therefore, we say that it is irreversible unless you add this large input of energy in order to get it back there. So any reversible process is at equilibrium. They can proceed back and forth, but there is no change in free energy. So if we do say something is at equilibrium, then that means that we are not looking at spontaneous and not. It is going to go back and forth between the two. There is no change in energy. But if it is spontaneous in one direction, then it will be spontaneous, non-spontaneous in the opposite direction. So that means that even though it kind of is a reversible process because we can go backwards, it most likely will not because we have to add a bunch of energy. So it will end up not ever reaching an equilibrium process. So spontaneous processes occur because they release energy from the system. We know if you release energy, that it is going to be exothermic because we are going from a higher potential energy to a lower potential energy. So it wants to release that energy. It is exothermic. There are some very few spontaneous processes that will be endothermic, that it will go from a lower potential energy to a higher potential energy. And it still can be spontaneous. We'll take a look in a minute at some examples, but this is very rare. Normally, we would think exothermic, giving off heat, right? That heat of our system helps us go forward in the reaction. We get a more energetically favorable process. It becomes more randomized. So, in order to determine if something is spontaneous, there are two different things you need to look at. So, before we talked about enthalpy change, we talked about if it was spontaneous based on is it a giving off energy or not. Our enthalpy change is the difference between our internal energy and our PV work of our reactants and products. So we did that last semester. We solved for that enthalpy change. Now we're looking at our entropy. So we're looking at the randomness between our reactants and our products. So our enthalpy, remember, we measured that in kilojoules per mole. So we looked normally. What we said was a reaction is exothermic if the bonds of the products are stronger than the bonds of the reactants. So that means that we wanted our bonds of our reactants to break. We made new bonds of our products. If our product bonds were stronger, we said that we now had a more stable molecule, and therefore it was exothermic. Exothermic, we know that means that energy was released, and so our delta H was a negative value. If it's endothermic, it's the opposite. That means that our bonds of our products were weaker than the bonds of our reactants. So energy has to be absorbed in order to make these new bonds. So our delta H is positive. The enthalpy change is favorable if we have an exothermic process. It would be unfavorable for an endothermic process. Things want to become more stable, right? We want to make more stable bonds. We do need some energy. Normally, energy would be released in order to make these bonds. And so normally we would say that that is a spontaneous process. That's how we did it last semester. But now we're going to be looking at the entropy. So entropy is a thermodynamic function that talks about what are the number of ways that are energy equivalent that we can rearrange our components. So our entropy does have units of joules per mole. So it is energy per mole. We do have an equation. It is the Boltzmann distribution, that we have some Boltzmann constant times our number of energetically ways of our system we can solve for entropy. We're not actually going to use this expression because it is extremely difficult to calculate W, and you'll see in a minute why. But we know that the more random a system is, it will require less energy than an ordered system because it's hard to keep things in order. It takes a lot of energy to keep it that way. It takes a lot of energy to keep your room clean, right? But it's a lot easier for it to randomly get dirty, right? It takes a lot less energy. So some examples of entropy: salt dissolving in water. Think about it. Salt is a crystal, NaCl. It's this highly packed crystalline form. What wants to happen is it wants to change into something that's very disordered. So it increases in disorder. There's an increase in entropy. So it is going to dissolve. This is actually an endothermic process. It does take in heat. Normally, we said endothermic processes last semester were not spontaneous. Well, this one we know is, because this one does end up increasing the disorder of the system, but it can also take in the heat of the surroundings in order to have enough energy for this reaction to occur. Another example of entropy, an increase in entropy, would be the evaporation of water, right? When it goes from a liquid, liquid is pretty stable, right? They're pretty close together, the molecules. Then it goes to something that's extremely disordered. Gas. We know gas molecules are floating all around. It's very disordered. So that would be an increase in entropy, would be going from a liquid to a gas.